another colleague from the School of Physical Sciences here in Dublin City University, and he's travelled a circuitous route to get here from Wisconsin originally, via Australia, and today he's going to talk to you a little bit about the fourth stage of matter, which I suppose to some of us who are not plasma physicists may be a little bit elusive. So today he's going to talk to you a little bit about plasmas. So I'll leave you in Bert's capable hands. Thank you.
Thank you, Siobhan, and thank you for the invitation to come. I will be talking about plasmas. But sort of first, I just want to talk a little bit about, which one? It's my own computer. I should know which button is the one that makes it work. Why am I a physicist? So I worked as an engineer for a number of years, and I realized that as I was working as an engineer, I kept asking, why does it work? Not just try to get it to work better, but I needed to know why. What was the phenomenology behind it? What could I see? What were the limits that were built into it? How far could I push something to the right or to the left, up or down? And it was something that, why I sort of left making lots of money in Silicon Valley and went back and did a PhD. I got into physics because I read an article in Scientific American as a senior in high school. And I read it, and having read several before, I read this one, and it was about plasma physics. I didn't know it was called plasma physics. And I said, that sounds like something fun to go do. And I started on that route expecting that I would change, because in the US you change 3 or 4 times as you're going through school, and ended up working in a lab as an undergraduate, and then went on from there to there and such. So be a little careful about what you introduce kids to, because you never know the slippery slope you'll set them down. So today, I'll just give you a quick introduction to plasma. I was trying to get it so something that you could do in transition year, and I think I've missed on that one. Apologies there. But we will do a little journey of discovery. I'll do some back of envelope calculations to give you a bit of a feel for what sorts of things you could talk about with your students. We'll see a couple of surprising results, and then I'll look at one particular application that I'm working on here. So basic states of matter. We've got a solid. As you add heat, you put energy in, eventually you break the chemical bonds, and now it turns into a liquid. As you continue to add heat, more energy goes in, you exceed the cohesive forces of that liquid, and now it is able to actually fly away again and turn into a gas. As we keep putting energy in, eventually we'll exceed the binding energy of an outer electron, so the atoms will be going so fast that when they hit each other, they'll have enough energy and they'll kick an electron out. And now suddenly we've got free electrons and ions and probably some neutrals left over still. And they start to behave differently when you apply forces to them. It actually behaves as a different material, and that's why we call it a fourth state of matter. So this is one of the ones that I have in my lab. It's about the size of a pizza oven, so 30 centimeters by 40 centimeters by maybe 10 centimeters in the direction you're looking into it. A couple of big windows so that you can look in and see. And sure enough, when we put power into it, we get light out, and it works. And so that was an argon, and here I've got the energy levels for argon. I've got ground state down here at 0 energy, and the ionization energy is 15.7 eV, and I've got to get it up to 15.7 eV in order to create that electron so that I can then excite everything and have it act as a plasma. But when you look at argon, the lowest excitation state is actually over 10 eV. So that means that first collision that's going to give you that electron off has to be at 10 eV. And 10 eV is 100,000 degrees Kelvin. And if I've got gas flying around at 100,000 degrees Kelvin, I don't think that's going to last inside my chamber. But it's there, and it works. So clearly, this picture of just putting in heat isn't really all that happens in most of these cases. And we need to take a step back and talk about the field that I work in, which we call low temperature plasma physics. It's basically a story of Newton and Coulomb, and that's about it. Actually, we'll need to do a little bit of Maxwell-Boltzmann, which I think is the part where I leave the leaving cert behind, but I'll show you when that part comes up. So we're going to assume that we've got a solution, that we're actually able to make this plasma. We see that it's there. There must be a solution. It's sort of the anthropomorphic principle, except for in terms of physics. We know that it works, so now we've got to figure out how do we describe it. And we're going to look for a solution that looks like low pressure, so 10 parts per million of an atmosphere. We're going to look at argon with neutrals, ions, and electrons. We're going to assume that we've got a small percentage of ionization. So in fact, it's mostly argon neutral, and I've just got a little bit of ions, say 1%. I'm getting light out, so I have to put energy in. I'm going to do that with an alternating current source. Again, we'll assume that it's steady state. So this is the situation we've got to do, and now we want to see how can we make this work? How can we describe the fact that we've actually got something there and it's not melting the aluminum chamber? In fact, inside the chamber I've got chunks of Teflon, and they're just fine. They don't burn, they don't get soft, they're okay. So we have to rethink the problem. And if I've got a plasma and I've got two electrodes that are facing the plasma, and I'm going to drive an AC current, so AC voltage, drive AC current through it, and that's how I'm going to put my power in. So I've got an electric field, and as a result, I'll have some current, and the total plasma current will be the sum of the different parts of the charged species that can move. So ions will move one direction in response to the electric field, and the electrons will move in the other direction. And we can say that the maths of that is the electric charge times the velocity of the ions, tells me what the ion current is, minus the electric charge times the velocity of the electrons, the minus of there, of course, because the electron's negative. And now we can go and use Newton and Coulomb here. And we know that the force that is being applied is just the charge times the electric field. But the force is also mass times acceleration. And we can then divide through by mass on both sides. And acceleration is just, where the acceleration is big, we're going to have large velocities as well. And so we'll end up with velocity being proportional to q over m times the electric field. But we've got electrons and ions. And my ions are, what, 80,000 times as heavy as the electrons. So, in fact, if we look at the electric field, we'll see that the current goes with it. The ions actually are much, much smaller in velocity, and therefore much smaller in current. And as a result, all the current is carried by the electrons. And so when I try to figure out how is the power getting coupled in, all the power goes into the electrons as well. So we've got power going into the electrons. Does it just spread out and heat up all the rest of the gas or not? We were talking about whether or not we could have atoms hitting each other hard enough to actually knock the electron off. But maybe the electron is going to actually heat these things up. And so we've got our fast electrons that we've, these hot ones that we've created through the plasma current. And now we want to see how much energy can we go from my screaming along fast little electron into my neutral or into my ion. And again, go back to the basic mechanics. Newton tells us conservation of momentum. Newton tells us conservation of energy, and you can solve for it. And we find out that the new velocity of the electron is, well, the mass of the electron is tiny in comparison to the mass of the ion, so I'm just going to ignore that, make that go to 0. And I'll do that top and bottom on both of them, and I end up with the velocity of the electron being exactly equal to the velocity that it came in with. It's basically a ping pong ball bouncing off a billiard ball, and it just bounces back. We maybe lose a little bit of energy. We might transfer a little bit of energy into the billiard ball, but in fact, there's very little velocity, and so when you look for the energy, velocity squared, it's really, really small. So electrons really don't lose much energy. The ions don't gain any energy. But if we were to solve this not for electrons onto these heavy masses, but if we wanted to look at energy transport between the ions and the neutrals, actually we find that we get very efficient energy transport. Two equal-sized billiard balls, and they transfer the energy very, very efficiently. So what have we done? Well, we assumed that we actually had a plasma and that we could look at it in the lab and say it was really there. And we thought about it a bit, looked at the current, the way that we power it, and we said, the current and the power really goes only into the electrons. And on collisions, the power stays in the electrons. So it's only the electrons that are getting hot, and the ions and the neutrals do not. Now, the electrons actually, we still have this problem that there's a 10 eV threshold before we get the first excitation state, and there's 15 eV before we ionize. And so somehow these electrons are going to have to get hot enough to where they can directly excite the argon up to ionization. And what ends up happening is we end up with, and it depends on some experimental conditions, like the size and the pressure of the gas and such, but we'll end up with the electron temperature being in the range of between 1 and 3 eV. And that means that in order to have a few electrons in our Maxwell-Boltzmann distribution that are out above the threshold, it'll be down by 4 or 5 or 6 E foldings in density. And as long as we've got enough of them there, then we'll sustain and we'll have a steady state plasma. Some of the plasma will move out and get lost to the walls, and we need to replace it equivalently. We are at steady state, so let's go and do a few little things about it. We know that 1/2 mass times the velocity is the amount of energy. That should be 3/2 kBt. If the ions are there at about room temperature, maybe they're a little bit warmer. Coulomb collisions, you end up with quite a few collisions actually to the ions. But we can substitute in for the temperature and the mass, and we find that the thermal velocity comes in at 425 meters a second. About what you expect. Sound speed, exactly what you expect for a room temperature moving gas, about the same mass as nitrogen or oxygen. My electrons are coming in at 2 to 3 eV, sort of a range. In plasma physics, we like to be within a factor of 2, so don't hold me to any more digits than that. Temperature 2 eV, mass 1/2 MeV per c squared, and when you solve for the velocity, you find out that they're moving at 10 to the 6 meters a second. So a substantial fraction of the speed of light. And that's just in my dumb little thing in the ground floor of physics. So those electrons are going to go really fast. And the ions are going to stick around and move really slowly. So we want to say, well, what happens if we take my box? Let's assume that I just magically create the plasma, fill it up everywhere. What does it look like? Well, I've got electrons, the little green ones. They're bouncing around, going in all different directions. I've got ions. I've multiplied all their lengths by, say, 1,000 or something like that so that we can see them at all. And that's what it looks like on the big picture. If we zoom in just on one little area going to the wall, we've got a whole bunch of little dots in there. I'm not sure that you can see those. Those are my ions. They're not moving. They're essentially still. 400 meters a second instead of 10 to the 6 meters a second. But the electrons, now I'm only plotting the x component of the electrons, and we've got essentially equal numbers going both directions. I'm now going to let time just move forward one click. When I let time move forward one click, then all the electrons that were in this distance, here's a wall, and all the electrons that are within the velocity in the x direction times that time step, whatever that click was. If they're inside that and they were moving to the right, they've gone to here and they've gotten lost. The ones that were over here that were moving to the right, they come across. The ones that were here and were moving to the left, they all move over. And the ones that were here in the wall, well, they stay there in the wall. And so suddenly now we've got a whole bunch of electrons here, an area where we still have the same number of ions, but the number of electrons has actually dropped by a factor of 2. We've only got half as many. And that means that we don't have charge balance anymore. If we plot versus position across here, so that's what I've plotted over here on the right-hand side, we can say what's the number of ions as we go across to the grounded plate over there on the side, and that's constant and flat. What does the number of electrons do? Well, on this part of the plasma, it's still the same, but inside this little slab here on the edge, it actually has dropped to half as big. Here we've got equal number of electrons and ions, and as a result there's no electric field. Over here suddenly we've got excess ions, and that means there's excess electric field lines from here going off to my ground. And if I integrate that, usually we say that the ground at here is at 0 volts. When I integrate that excess charge, I actually find out that there's a potential difference between the bulk plasma and this edge, and that electric field is actually pointing in the direction from the bulk plasma out to the edge. And so we've got a drop in potential as we go out. And that means that positive ions, when they see this edge, they get here, and as they cross over, they see an electric field, and they'll be accelerated out. They'll fall down that potential hill. The electrons see that as a potential hill because they're negatively charged, and most of them will actually be reflected back. So the ions, once they hit this boundary, they're going to go. The electrons, some of them at least, will come around and come back. We've got, still have our power going in over here somewhere, so making as many electron ions as we're losing. But we need to look and see how, we want it to be steady state. We need to actually, I said that the ions aren't moving, but in fact, eventually the ions will move. They'll see this electric field and they'll go out. And I need the number of electrons and number of ions to leave at the same rate. So is there a solution to this? And we need the electron loss and the ion loss to be the same. Now our electron flux, it's being pushed back by this electric field. So the total number of electrons we have is 1/4 NV bar, but we have to multiply by this Maxwell-Boltzmann distribution. We've got this a number of particles versus the amount of energy that they have. We've got an electric field that's pushing a lot of them back, and it's only the ones that are going along with a high enough energy in that direction that can go over that barrier and make it out to the wall. All of these electrons get pushed back, and only this tail component get lost. On the ions, well, the ions are 1/4, well, actually, it's not 1/4 because every one that hits that boundary falls out. As soon as it gets there, it doesn't matter what direction its velocity was, if it somehow got there, it'll be attracted by the electric field and out it goes. So it's just N times V. We can set those two equal to each other, and we can actually solve for the potential difference that we need to have in order to have steady state, for the flux of the ions and the flux of the electrons to be the same. And we end up with the potential. Well, it depends on the electron temperature. That makes sort of sense. The faster they were going, the more you have to push them back to slow them down. And then it depends on the ratio of the masses as well. And we end up with something that says it's the electron temperature times, plug all those numbers in here, you end up with about 6.5, somewhere between 5 and 10 for most species. This is 2 to 3 eV times somewhere between 5 and 10. The plasma, this potential difference between the plasma and the boundary is going to be on the order of 10 to 20, maybe 30 eV. Depends on the gas, depends on the operating conditions. That's a big enough barrier so that the electrons that are trying to get out and get bounced back are maybe just about able to actually ionize the argon. So what we've got is we've got a case where we're coupling power into the electrons. The electrons aren't losing power to anything else. The plasma self-organizes into this case where there's a voltage difference between the plasma and the boundary. We call this a sheath. It just covers the whole outside. And the sheath serves to, what we say, insulate the bulk of the electrons from the wall. The electrons are trying to get out to the wall, and the heat that they're carrying is being reflected back in to the bulk system. The sheath also accelerates ions from the plasma out into the surface. And so they actually strike onto the surface with a substantial amount of energy, sort of on the order of 15 eV, whatever that potential difference within the plasma is. So they come in and they can strike the surface and drive chemical reactions there on the surface. I told you that I was going to tell you about exotic chemistry, and we just don't actually have time. So we can talk more about that later on if you wish. What I do want to talk about is one of the applications that we're working on. So we're using plasmas, and one of the things that's coming down the technological pipeline are flexible displays. We've got small ones already. There's one from Samsung or Nokia in the top, and here's one from Arizona State University. They've been working on flexible displays for a while. There's a bunch of reasons why we'd like to move from glass displays to flexible displays. There's less breakage both when you're making them and when you're using them. If you've seen these 10,000 euro Samsung displays that actually warp around you so you can sit in the sweet spot and have everything look right? What if that was $499? That'd be all right. At the moment, Samsung's yielding about 3%, and I think LG's yielding about 5% on those displays. 95% of what they put into the pipeline, they throw away before they get to the end. If they could do, because the glass breaks, they have to go to extra thin glass to make it warpable. So you also can build cheaper, lighter frames. Have you heard about the fact that the iPhone is now warping and people are ending up, they put it in their pocket? They put it in their pocket and they take it out at the end of the day and it's no longer flat. Well, it would almost be a feature if they just had a flexible display. It'll go in your pocket, it'll fit nice, it'll work. So the Samsung thinks that they can cut 40% of the cost and 40% of the weight if they can get a flexible display, because the frame is that much cheaper, that much easier to do. But if you're going to build electronics on plastic, actually it turns out plastic is, we tend to think of it as holding water, but it doesn't. It actually leaks water. And with these OLED displays like you have in an iPhone and all the top ones, these bright, rich colors, they're really, really hypersensitive to water. So we need to put a layer over the top of this plastic that keeps the water out so that the display will continue to work. And what we do is we put in silane gas, ammonia gas, a bit of nitrogen, we run it through the plasma excites all these species, the silicon sticks to the bottom to wherever we're building our display on, and the nitrogen comes in and says, oh, silicon there, I'd like to bond to you. And now you grow a layer of silicon nitride. And that works great, except you have to be at hot temperatures. When you do this, it's the ammonia that gives you the nitrogen, it's the silane that gives you the silicon, and they both bring hydrogen in with them. And you end up with a bunch of porous structures in there. There's a bunch of extra hydrogen, what we call interstitial hydrogen, and that creates circuitous paths for water vapor to get sucked through. And so that's not okay. It's not so bad for glass because they can run it over 300 degrees, and at 300 degrees it anneals out as they grow it, and the hydrogen comes out. But at plastic, if we run it at 300 degrees, it's not so happy. That's how it works. N2 is a miserable species to try to make into silicon nitride because it's such a strong bond. You really can't ever get activated nitrogen to get incorporated, to react with the silicon and incorporate into your film. So we end up paying for ammonia. We have to pay for it on the way in. We've got to pay to burn it on the way out and make it safe before we release it to the air. The silane as well, we've got to pay for that, and then we've got to make sure that it's all burned and dealt with on the way out. So those are costs to us. And at the moment, they're using a very small fraction, somewhere between 5 and 10% of the gas that they put in actually gets onto the substrate. You'd like 50%, half on the bottom, half on the other walls, but they can't do it. So we got some funding from the South Korean government to test some technology that I had developed. And so we've got a different way of creating a plasma. And we think maybe it'll be better. There's other people that think it'll be better too, but it's a little bit unclear. Basically, some people put a certain frequency through to drive the current. And instead of running at 10 megahertz like most people do, I run at 160. That's all I do that's different. But the way it actually deposits power into the plasma ends up being different. We use what's called high VHF current, so it's up higher than the FM radio, not quite as high as the VHF old TV. If any of you are old enough to remember tuning in the VHF stations, those are a little higher than where we are. But there's a bit of a problem. High frequency chemistry is what we call it in industry, and nobody really knows what it is. And some chambers that look like they should have it do, and some don't. And we don't know whether mine does, and we don't know whether or not even having it would be good for this process. So we're sort of running out on a limb here. So we've done some, the guys in Korea, we do pretty much the hardware and we do the plasma physics of what's going on, and then they run the process and try to figure out, can they make it to where it'll satisfy Samsung. And so they've done these things. I don't know if any of you read Korean. I don't read Korean either. But what it is we're trying to do is we want to have, this as thickness versus the ratio. We've got a fixed amount of silane and we're changing how much ammonia we have to put in order to, and then that changes the type of film we get. Whether we have excess amounts of silicon or excess amount of nitrogen in there, and that also helps you determine how porous the film is and how much water is going to leak through. And then the other thing we can do is we can measure the reactive index of this thin layer that we're growing, and we want to end up with a reactive index of about 1.77. That's what we would like to see. And we can, there's some funny things over here on the left. Actually, those first 3 data points, they thought were really good, and we were able to show through plasma physics that they're trash. They're no good at all. The whole plasma is flickering on and off. It's also pretty low dep rate, which is because the plasma was flickering on and off. It was flickering faster than we could see with our eyes, but when we did electrically, we could see. As we add more nitrogen, we grow faster and faster, but we end up with a film that has too much nitrogen in it. And so instead of being a nice crystal, it's got a bunch of open pockets where the nitrogen is holding on to hydrogens, and the water will get sucked through there, those capillary reactions, essentially. But we can get a region where we've got a good dep rate, good thickness for amount of time grown, and also the index of refraction comes in right where we want it. And that's really nice. It's 5 times as fast as they expect for the amount of silicon that we're putting in. And we're using about a third to a quarter as much ammonia as goes in. So we're able to activate those gas species. We went and did another measurement where we can look with Fourier transform infrared, and we can say, what is the types of bonds that we have in our system? We've got silicon, nitrogen, and hydrogen. We want to know how much silicon is attached to the hydrogen, how much nitrogen is attached to the hydrogen, or hydrogen is attached to each of those. And we can actually go and calculate what is the number density that we have in there. And we end up with numbers at about 5 times 10 to the minus 18. That must be 10 to the plus 18 per square centimeter, actually. And actually, they're really happy with that. That's quite low hydrogen density considering. And the question is, why are we doing so well? if we have nitrogen, that's this N2 molecule, I was telling you it was really strongly bonded and you can't break it apart. Well, it turns out that we're able to take this nitrogen, this is versus the bonding radius, and this shows the different vibrational energy levels. So this is quantum mechanics, something I never thought as a plasma physicist I'd use. And if we move it to an excited electronic state, that's this one up here on the top, when it goes from the ground state up to the top, it doesn't end up in the, it starts at the lowest vibrational level, and when it goes up to a new electronically excited state, it has to go into a really high vibrational level. And then when it decays back down, there's a good chance that it comes back down in another high vibrational level. So we think maybe we could be producing really vibrationally excited nitrogen. That means the nitrogen would bring energy into the surface, and that means the nitrogen could actually drive chemical reactions and cause itself to be incorporated into the surface. So we looked at some literature, and this is some group from Japan, and they looked at, as a function of driving frequency, and they looked at the vibrational temperature, and they see that the vibrational, so we've got gas temperature of about 300 K, and they've got vibrational temperatures of 3,000 to 4,000. And when we go and look at our system running at 162 rather than 13 megahertz, we end up with values between 6,500 and 7,500. And that means that it's carrying a lot of energy. So maybe that's what's going on. To summarize, plasmas create an exotic chemical environment. They have a wide array of applications. Fundamental understanding is really just Coulomb, Newton, and a bit of Maxwell-Boltzmann, which is a bit beyond, I think. Maybe you do it in chemistry, but certainly not, I think, in physics. I'll work on it. Maybe I can come back with a way of describing it using leaving cert physics. There's a lot of technological applications driving this plasma, what we're learning in plasma physics. And they go way from one side to the other side. Very mature and technologically demanding semiconductor manufacturing. Intel uses plasmas for more than a third of the steps to create their chips. And then there's new areas like plasma medicine. And the fundamental physics is actually critical to getting these applications to succeed. Lots of jobs and good money for students as well. That's it. Thank you.